Welcome to the Oxygen Alliance YouTube channel, where we bring you videos on installation, maintenance, and various trainings on oxygen equipment and devices. If you have comments and/or questions, drop them in the comment section below or write to us info@oxygenalliance.org. Remember to like our videos, subscribe to our channel, and hit the notification bell.
Hello everyone, thank you for joining us for this week's Oxygen Talk Call brought to you by Oxygen Alliance. My name is Sharon Wozo and I'll be your host today. If you're just joining us for the first time, the Oxygen Talk is a radio meeting that the Oxygen Alliance hosts every second and fourth Thursday of the month, 2 to 3 p.m. Central African time. So in these talks, we have one talk that our technicians from OpenO2 and Sunline, they present to us a topic that they've prepared. And on the other talk, we have our partners presenting to us information that they prepared for us as well. And today, our biomedical engineers from OpenO2, they'll be presenting to us about anesthesia technology. So if you have any questions for us regarding whatever we talked about in the presentation, please, you can write it down. And at the end, we'll have some time where questions can be asked, or you can paste them in the chat and then I'll read them out to you. So for our new members, do paste in the chat your email address so that we can add you to our emailing list. So reaching this far, I'll hand it over to our technician. Over to you, Emmanuel.
Thank you very much, Sharon. And indeed, today we'll be looking at the anesthesia technology. So we'll focus mainly on the Gloucester vent helix. And let's go to the next slide. An anesthetic machine is basically a machine that is used by anesthesiologists and then or a nursing anesthetist to support the administration of anesthesia. And of course, these machines, they also come with other functions like oxygenation, the accurate mixture of anesthetic vapors, appropriate ventilation, and also helps to reduce contact between the anesthetic vapors and the anesthetist. Let's go to the next slide. So in this presentation, we have split our presentation into two. We'll discuss the first part, whereby we'll be dealing with the Gloucester vent helix, mainly because it's the common model in most low-resource countries and, of course, some medium-income countries. And then we'll have another session where we'll discuss the universal anesthesia machine. And to help our audience understand better, we have split this presentation into two parts. So we'll discuss the electrical part, and also we'll go to discuss the pneumatics part. Taking us through the electrical aspect is Foster Central. So at this point in time, let me hand over to Foster Central to present the first part of our presentation. Thank you.
Thank you very much, Emmanuel. My name is Foster Sentala, and I'll be taking you through the first part of this presentation, which covers the electrical aspects. To begin with, I'll introduce to you some of the parts of this anesthesia machine that we're looking at today. So as you can see on the diagram, the part number one is a low resistant vaporizer. So this one is where you put your anesthetic agent, the one that you want to be vaporized to be sent to the patient. You also have number two, which is a ventilator, a gas-driven ventilator that functions even in the absence of electricity. The third one is an oxygen concentrator, which produces oxygen and air for the patient to breathe and oxygen to drive the ventilator. We also have part number four, which is an integrated method of manual assisted ventilation that can be taken to the patient side. We also have the gadget number five, which is an oxygen analyzer that indicates the concentration of oxygen being delivered to the patient. Apart from this, we also have other parts that are shown, that are listed on the next slide. So we have, like in this case, the scavenger. We also have an interruptible power supply unit known as the UPS. So these parts, not all of them are electrically driven. Some of them don't require electricity to operate. For example, the vaporizer. So I'll be taking you through the parts that usually need electricity to run. I have listed a number of supply systems, the systems that supply power to our machine. So these machines belong to what is known as class 1 of medical electrical equipment. This is to say that these machines do not only rely on basic insulation for protection against shock, but they also rely on protective earth ground for the parts that are accessible to the users. So the main supply for this machine is the mains electricity source, which supplies 230 volts and on a frequency of 50 hertz. And this power is recommended to be supplied via a UPS. This is so because the UPS serves as a voltage regulator, stabilizing all the voltages and also protecting the machine from electricity surges. This also provides a battery backup for at least 30 minutes of run when there is a power failure. And the UPS that is supplied by this gross event unit usually comes with 2 modes. The first one is bypass mode. The second one is line mode. On bypass mode, you are not necessarily using it as a backup power, but you're only using it as a voltage stabilizer. So if you want to use the UPS as a backup, you have to activate the line mode. This is done by simply holding the power button for at least 5 seconds until you see line mode displayed on the LCD. Moving on to the next slide, we have outlined some of the other power sources alternatives. So in cases whereby the UPS has been completely discharged, as well as in cases where there's power failure, the system also incorporates the use of a ventilation backup. So this backup is supplying 12 volts DC to specifically the ventilator as well as the scavenger unit. This backup of 12 volts battery may last to about 12 hours of use without including the use of the oxygen concentrator. We also have oxygen backup. This is by the oxygen cylinders that are connected at the back of the machine. In cases whereby this 12 volts battery has been used up, there is also manual ventilation, which can also be a substitute of the gas-driven ventilation. So you can employ the use of manual ventilation in cases whereby the UPS and the 12 volts battery have been discharged. Moving on, we have this electrical flow diagram simply outlining the way current flows in our unit. So this is a general flow diagram of several machines. Some parts of this diagram might differ in other machine models. So when you see on your left upper corner, that's where you're connecting the machine to the mains supply. And from the mains, you can connect either a UPS or an AVS, which is an automatic voltage stabilizer or voltage switcher. This is put there just to protect the machine from surges by stabilizing voltages. So you can see there's also, after this, the mains isolator switch, there is a 24 power supply unit that is tapping from the mains line. This is supplying DC voltage to the control board. On the control board, we have the analyzer circuit, which is placed in the front of the machine. This analyzer simply analyzes the concentration of oxygen being delivered to the patient. Below the control board, there is a pressure sensor, which senses or displays the amount of pressure being delivered to the patient. So in cases whereby there's low pressure or high pressures, these are displayed by the systems of the LEDs that have been put on the machine. There's also a speaker that in cases whereby there are abnormal conditions, the speaker usually buzzes out. Below this diagram, there is an oxygen concentrator, which is tapping directly from the AVS or the UPS. And inside this concentrator, there's also a 9 volts battery. This battery is put there just to provide power to the alarms in cases whereby there's a power failure. So when there is no electricity supplying the oxygen concentrator, this battery supplies this voltage for the alarms to sound. Moving on, this machine has several indications in cases of power failure. So the first one is indicated on the UPS. So when power is disconnected, there is usually an alarm that sounds on the UPS. So in cases whereby you hear the UPS beeping, you have to check with your connection from the mains. There is also, as I've said earlier on, there's also an alarm on the concentrator. So you have also to check the connection from the mains or from the UPS. If there is power cut, then you have to find alternative sources. There's also, if there is a chance that you're using a patient monitor connected to the UPS or directly from the mains, there's also usually an alarm that is also placed on these patient monitors. Most of them come with an internal battery, but you might also still want to consider revising your power supply in cases whereby these batteries run out. Moving on. On this slide, I would like us just to have a look on some of the things that might need to be replaced with time. So to your left, there is the fuse that is placed on the control board for the ventilator unit. So in cases whereby the ventilator is not switching on, you might consider checking this fuse. It's easy to replace. You just pull it out of the holders and then replace with a recommended rating, in this case 2 amps fuse. There is also a 12 volts battery that is supplied with the unit as backup. In cases whereby you have noticed that the battery is not lasting as expected, maybe less than 10 hours or less than that, you might also want to consider replacing this battery. So you just need to have a replacement battery with the rating of 12 volts and at least 10 ampere hour as capacity. There's also a fuse before the battery. It's also rated 2 amps. In cases whereby the battery has been discharged and it's no longer recharging, you might also consider changing this fuse. Reaching this far, this is some of the parts that I wanted us to look at on the electrical aspects of our Grosvenor Helix unit. So my colleague Boniface will continue the presentation and he'll be discussing on the pneumatics part of this machine. Thank you.
Thank you so much, Foster. My name is Boniface Kaseka, and I'll take you through the general anesthesia pneumatic part. So generally, when we are talking about the pneumatic system, we're talking about pressure, the gases, as well as the liquids that are involved. and the safety measures that are put in place to make sure that these parameters work in conjunction with each other. So first of all, we have to talk about the anesthesia machine and the pneumatic system and how it is divided. So it is divided into three basic areas. So we have a high pressure system, which consists of gas cylinders. So it is called a high pressure system because the gases that are in gas cylinders are usually at a higher pressure. So here we're talking about pressures that are greater than 10,000 kilopascals, or we're talking about 22,000 psi. Then the second area is the intermediate pressure system. So this is where we are talking about the gas that is drawn from the hospital pipeline, or in other cases where the anesthesia machine can incorporate the use of an oxygen concentrator. So the gases in this system are usually at pressure of about 45 to 50 psi. So that's why it's called an intermediate system. And the low pressure system, we're talking about gases that are below 26 psi. So we look at the different pressure systems and how they work in an anesthesia machine. Next slide. So this is a simplified pneumatic schematic diagram of a normal anesthesia machine. Of course, different brands will have different modifications, but this is just the general one. So if you look to your left, we have the high pressure system. So in this high pressure system, as I've already said, you have cylinders. So in a case whereby there's no pipeline oxygen or nitrous oxide from the hospitals, most anesthesia machines do use cylinders, which are usually attached at the back of the machine. So we can see that there's an oxygen as well as nitrous oxide cylinders. And after that, we have the check valves. The check valves are one-way valves. They simply avoid rather the backflow of the gases into the atmosphere or into the cylinder itself. And moving on, we have a pressure gauge. The pressure gauge indicates the pressures that are available in the cylinders. So another thing to note is that nitrous oxide in cylinders is available in two different forms. So you have a liquid as well as gases. So when you start drawing the gas from the nitrous oxide cylinder, the pressure does not change because the liquid just it changes to gases. So the pressure remains the same. So the moment you see there's a decrease in the value of the nitrous oxide, because the nitrous oxide is about 745 psi. So the moment you see 740 and below, it means that it is about to empty up. Whereas when you're looking at the oxygen, the pressures, it's about 2000 psi. So that will not be a problem. However, as I've already said, it is a higher pressure, and this pressure cannot be maintained by the machine. That's why you have a pressure regulator right there. So the pressure regulator simply sets the pressures at a lower value. So from the 2,700 something values, it sets them to 45 rather, up to 50, depending on the model of the anesthesia machine. So that's where you go into the intermediate system. So from the intermediate system, if you're not using the pipeline, it flows up until to the flow meter. And before the flow meter, you'll see that there's an oxygen failure alarm. So the oxygen failure alarm indicates at times whereby there's a leakage and the value has dropped up to less than 18 psi. So another thing to note is that when oxygen, the nitrous oxide depends on the pressure of oxygen. So if you have a low pressure of oxygen, it means that it is in low supply. And as that, you cannot administer it to a patient because you can create a condition that we call a hypoxia, whereby you have a less than less than 21% of oxygen, and that can be toxic to a patient. So most anesthesia machines have what we call a reservoir. So if you have an alarm indicating that you have low amount of oxygen, you can simply just use the reservoir to accommodate for the lost oxygen. And another feature that you have seen there is the nitrous oxide cutoff. Like I've already said, that if you have low pressures of oxygen, then you can't administer, it's not recommended to administer the nitrous oxide to a patient. So this mechanism is just used to do the function of removing, of cutting off the nitrous oxide when it has shown that the oxygen levels or the pressures, they are very low. So from the intermediate system, the gases flow into the flow meter. So the flow meter just simply indicates the flow rate of the different gases. And from there, that's when you go into the low pressure system. So you have valves that reduce the values of, the pressure. So from 50 or 45 up until 14 to 26, depending on the ratio of the different gases that each machine uses. And from then on, it goes into the vaporizer. So the vaporizer contains anesthetic gas, so it can either be isoflurane or it can be halogen. So from then on, that's when it is administered into a circuit, the breathing circuit rather, and that's completing the pneumatic system. Of course, if you're also using a pipeline oxygen, it simply means that you ignore the high pressure system. So you go from the pipeline, then you go into the cutoff, the flow meter, as well as into the vaporizer. So another feature that you can see there is the oxygen flash. This is simply used to administer oxygen at a high pressure into the breathing circuit. So you are bypassing the flow meter, you are bypassing the vaporizer and the other gases. So you are just delivering the 100% of oxygen into the breathing circuit. Of course, the function differ with different types of different models of anesthesia machine, as my colleague will explain further when we go deeper into our machine. So another thing that I would like to look into is what are the safety measures that are placed to make sure that, for example, you don't administer the wrong cylinder or you don't have the wrong pipeline of gas and administered into the machine. So the next slides, we're going to look at those features, some of the features rather, because they're a lot. So as I've already said, we're going to look at the high pressure system. So this one is the one that contains the cylinders. And what are the safety measures that it has to make sure that you don't administer the wrong gases? So I've already talked about the pressure indicators as well as the pressure regulators and how they function. Another thing that the machine has is what we call the pin index system. Of course, another safety precaution that we can use is the color coding of the different cylinders. So for example, when you're talking about oxygen, the color coding is normally white shoulder and black body, whereas for nitrous oxide, it's normally blue. Of course, it depends on the country color code, but universally, those are the colors. So now we're going to look at the yoke assembly. So the yoke is present at the back of the machine. Its main function is to rather support the cylinder. It also provides a gas tight seal, which is called a Bodock seal. This is to prevent the backflow of gases, as I've already mentioned. And it also has what we call, it prevents the cylinder being attached to the long inlet. So this is what we call an index pin system. So this is what I'll explain a little bit further, the index system, in the next slide. So the index system goes like each and every yoke has what we have pins. They are about 4 millimeter in diameter and 6 millimeter in long. So what happens is that each and every yoke has its specific number and placement of these pins that are protruding. In correspondence, each and every gas cylinder has a corresponding hose that correspond to those pins. So for example, if you are talking about oxygen, that means oxygen has its own placement of hose which are different from nitrous oxide. So if you put a wrong cylinder, it means that it will not fit. As you can see there, it has to align. So if it doesn't fit, that means it is an indication that you are using the wrong gas for the intended purpose. So if you look into the next slide, as I've already said, it says oxygen has spin index of 2 and 5. So universally, each and every oxygen cylinder will have the pin of 2 and 5. And each and every machine, an anesthesia machine, will have a yoke with a 2 and 5 pins. So that means they will only correspond to an oxygen. For the nitrous oxide, it has it has pins 3 and 5, and that's universal. If you for each and every anesthesia machine, it means the yoke will also have the protruding pins of 3 and 5. So this is simply to make sure that you don't use the wrong cylinder to administer the wrong gas. So another thing that we're going to look at is when we are using the pipeline system. So as I've already said, the pipeline system, it's the one that is used in hospitals. So here you're using the hose pipes. And of course, at the end of the hose pipes, we have what we call the probes. These are the shredder probes. So these probes are of different diameters to correspond to the gas that they are administering and that they are transferring. So this is just another safety precaution to avoid the administration of the wrong gas. And another thing that you have noticed on the picture is that they have different colors. So for oxygen, it has its own, the hose pipe has its own color. For nitrous oxide, it also has its color, and other gases have also their own color. So you have those protruding collars that are called shoulder probes, and also on the walls they have corresponding shredder sockets. So this simply to mean that if, for example, you use the oxygen probe on a nitrous probe, it will not fit because the diameters and the structures, they are different. So this is just another way of making sure that we don't use the wrong, you're not administering the wrong gas. So if we go to the next slide, you appreciate what I'm talking about. As we can see there, you have the nitrous oxide. The diameter is different from the one that you can use for oxygen. Of course, there are so many features, but these are the ones that I have exhausted for you right now. And from then on, I will have to ask my colleague, Emmanuel Chauya, to talk more about the anesthesia machine that we're talking about in this call. So over to you, Emmanuel.
Thank you so much, Boniface. And like Boniface has hinted on, I'll just be explaining on the model that we're discussing, the cluster vent helix, with respect to the outlined general schematic. So what you see in your visual is a schematic specifically for the cluster vent helix, and to your right is the actual cluster vent helix. I'll start with the number 1, which is at the very bottom, the biggest blue cycle, yes, there. So this is an oxygen concentrator. You can check with the diagram to your right. And this concentrator is made in a way that you have 2 outputs. So you have oxygen and also compressed air. So the path that you see in black is the one that carries the compressed air, whilst the blue line carries the oxygen line. So to your bottom left, there's 3 and 4. These are the connections that Boniface referred to, where you can connect oxygen cylinders, and of course the normal hospital pipeline. So depending on what is available, you can connect. But this model is mainly designed to be used in situations where you don't have power or you have intermittent power supply. That's why, as Foster hinted on, it comes with a backup system. So let's follow the pneumatic path. You would see that as we go up the path of oxygen after the label number 19, there's a diversion to 14, and then just up there, uh, the two that you see up there, labeled 6, are flow meters. So these are the ones that give control to the user to administer what volume per minute of oxygen or air. So it is also worth hinting on that the maximum you can get is 10 liters per minute on this model. And the bypass route, it's referred to as the flash line. So this mainly is used to flush the whole pneumatic system of excess maybe or residual vaporized um, the isoflurane or the halogen. So when you want to change, let's say you want to change the vaporizer, which we'll look into just in a moment, to sevoflurane, you would have to flush the whole system. So you use the button 15. And after the 15 button, you can see there is a green bag, and also it appears on the image to your right. This is the reservoir bag. So the volume is 2 liters, and mainly it's there to just contain oxygen that can be used to compensate in times where you have maybe a low flow or indeed a complete shutdown. This machine, more or less, also just like many other anesthetic machines, has the capacity to draw in normal air. So this is indicated by the indication number 11, where there is a valve. So when you have a deficit in the set volume that you want to administer, let's say you wanted to administer maybe 2 liters of oxygen, and then you have 1.5 or 1 liter, then this system would compensate by opening the valve to draw in normal air. It is also worth mentioning that there's a control mechanism whereby you can only have 5 centimeters of water going to the patient in the pipeline. So this is achieved by having a valve also which will open to release extra pressure so that you maintain this threshold. We'll look into it in a moment. So the gas in the pipeline, you can also monitor. There's an independent oxygen analyzer, and this one you can do with or without it. But it's always advisable to do with it because it gives you an idea of what concentration of oxygen are you giving to the patient. So we'll also see how we can calibrate the same. Then we have the vaporizer at point 10. Let's also note that this vaporizer can be for isoflurane or halogen or sevoflurane. So halogen and isoflurane can be used in the same vaporizer, but if you're using sevoflurane, this machine comes with a separate vaporizer, or at times if it doesn't come with it, you can request from the supplier to supply you with the same. So after the vaporizer, that's when the pipeline leads to the ventilator or to the patient or even to the self-inflating bag. If you follow the red line below there's written 7. This is just to help in manual ventilation, which we'll look in a moment. So maybe you can want to operate this machine where you don't have power and then the UPS has run out, but you still want to do your OR procedures. You would use this and administer the normal air to the patient. To your right, you see number 2, this is the helix ventilator. Primarily why the machine was named as the Gloucester vent helix, because it helps you to control the tidal volume that you administer to the patient. So we can say maybe it's a semi-manual kind of, whereby you have to manually adjust or screw in the helix screw to the desired volume. And then when the gas is filling the bellows, it will only go up to that far and deflate just like that. Let's go to the next slide. Okay, so this is a closed loop up on the interface. Like I was hinting on, you have the oxygen flow meter, the compressed air flow meter. You have up there what is labeled as 5 centimeters of water. This is the relief valve to just limit as to how much of the pressure you can give to the patient. And also, the red button is the oxygen flush as indicated. Then you have the vaporizer to your right is the ventilator, the helix ventilator. Let's go to the next slide. Next slide. Okay, thank you. So, yes, on the interface also down there, this is where you have most of your electrical and of course partially the pneumatic control. So we'll start with the left corner, and this one is the on and off knob. So you rotate it to the on position, you switch on all the electrical connections. And the next one is the trigger knob. This is where you set your threshold for the alarm, the pressure alarm, whether it should buzz and light up at 5 centimeters or any other set threshold. Breaths per minute. So here you control as to how often and how slow or how fast should the bellows be going up and down, thereby also controlling the breath rate of your patient. And just up this knob, you have the patient pressure control. So when you are rotating this clock or anti-clockwise, you'll be adjusting the pressure, and you can see in real time on the pressure gauge. To your right, you have the outlets and of course the return line. This is where you have the Y-piece connection. Let's go to the next slide, where you tap from this and then you give to your patient. So the patient can inspire through the inspiration line and then expire through the other. Of course, there are valves there to control all this. The Gloucester vent helix anesthesia machine comes with a manual bag that you can use to manually ventilate your patient, as I hinted on earlier. And also you have automatic, or what is otherwise referred to as continuous ventilation by the bellows, the helix ventilator. Let's proceed to the next slide. So a quick analysis of the patient circuit. You have important components like the adjustable pressure limiting, which we just saw that you can actually control the pressure threshold, and it ranges from 1 centimeter of water to 60 centimeters. And of course, we have already hinted on that. The recommended or the most common threshold is the 5 centimeters of water. And then you have a reservoir bag, and you have the Y-piece connection, which for adults would have a diameter of 20 millimeters, and for pediatrics you'd have 18 millimeters. Then you have a mask or cannula that you interface your outputs with the patient, and you have a scavenger system. And on this machine, it comes with a switch which you would have to manually switch on, and then the fan would rotate, drawing in the expired carbon dioxide to the atmosphere. Let's go to the next slide. So in this next slide, I'm just hinting on that the anesthesia machine also works hand in hand with the patient monitor. Of course, in our subsequent talks, we'll be diverging much into most of these equipment, so you may wish to hang around more. But on the patient monitor, just in a nutshell, you can monitor the oxygen concentration in the patient's blood. You can monitor the blood pressure. You can monitor the temperature in real time, pulse rates, and of course, you can also capture the ECG. These are essential parameters that helps the anesthetist know what to do at a particular time during the procedure. And let's go to the next slide. I will talk about the calibration of this machine, but before I do that, just to invite you to write in the comment box of the common brands that you have in your country. Do you have this brand that you are discussing, or maybe you have any other more brands? Like we hinted on, our next presentation, we'll be talking about the universal anesthesia machine. So maybe you have that or any other brand. This information is very essential, and also please write where you are joining us from so that we know. And to calibrate, as I said, the oxygen analyzer is a partially standalone system. So you just connect it to the pipeline, but you can calibrate it. And to calibrate it, you use normal air to do that. So as I said, this machine comes with an oxygen concentrator, and the oxygen concentrator has two outputs, the oxygen and also the compressed air. Now, to use the compressed air in calibration, you would have to completely shut down or lower to zero the flow meter for the oxygen so that you only have compressed air in the pipeline. And then when you do that, at least at 5 liters per minute, you press calibrate on the oxygen analyzer and you let it calibrate. And once it's done, then it captures the concentration that's in the room air, usually 20.95 or 21%. Let's go to the next slide. So my colleague will be discussing the alarms and error codes, and this helps also to troubleshoot for most of our audience here. So over to you, Elizabeth.
Thank you, Emmanuel. My name is Elizabeth Tabalaba, and I will take you through the last part of our presentation, which will include alarm and error codes, troubleshooting, and the routine maintenance of the anesthesia machine. So the Groster vent helix anesthesia machine has different alarm modes, which include the low pressure or disconnect mode, high pressure modes, low battery level mode, as well as the battery failure mode. So the alarms give an alert to the user on how audible the alarm should be and the color of the LED, as well as the mode in which the LED will be lighting under different levels of priority. To begin with, I'll just explain how the low pressure or disconnect mode works on the machine, whereby it is represented by a red LED that is actually intermittent flashing for 15 seconds. And after 15 seconds, it then changed to just constant lighting. And then when it reaches almost 20 seconds, it is followed by an audible alarm, which is of sound level greater than 45 decibel. And going ahead with the high pressure alarm mode, this one is represented by a red LED, actually that is constant, followed by also a constant audible alarm. And the low battery level mode alarm, this one is represented by a green flashing LED that is not accompanied by any audible alarm. Actually, The LED flashes when the battery level running hour is less than 2 hours. And finally, with the battery failure, we were able to know the alarm or the error code by just a constant audible sound, and there is no LED showing any indication. Actually, the battery failure is activated when the battery capacity is no longer sufficient to run the solenoids. And when that happens, also the bellows cease to operate. So all the audible alarms that actually happen, they happen at a sound level, sorry for the inconvenience, of greater than 45 decibels. So this condition whereby we are having the alarm as well as the LED showing up, it is actually clarified to be under the medium priority, whereby the one that is not having any audible alarm, it is categorized to be of low priority. In the next slide, we want us to understand and even appreciate of the alarm modes that I was talking about, whereby from the left picture, we can see that we're having the high pressure and low pressure LED indication, and we're also having the alarm mute button, which is used to silence the alarms. And to our right side, we're having the alarm indicators over an oxygen concentrator. This one actually shows the low purity, any power disconnection, and also we're having the hour meter, which shows the time at which the oxygen concentrator has been running to, and also a reset pin. Moving forward, we just want us to understand that it is actually good that the unit should be positioned adjacent to the patient, such that the operator's eye line is within the 120-degree sweep angle in front of the helix machine to ensure clear vision of all warning lights. Now, moving forward to alarms or situations that will require immediate attention of the anesthetist or technicians, we can have a condition whereby we have low oxygen warning light on the concentrator, and it starts to illuminate. This many times happens when we are having a filter being obstructed, and also many times it is due to a condition whereby we are having the degraded zeolite in the sieve beds. To solve this problem, we'll just change the filter and wash it and replace it back. And also for the zeolite problems, it means we need to replace the sieve bed with new functioning zeolite. Going ahead, we can also have an alarm whereby we have a low pressure alarm sounding on the ventilator and warning light also illuminated. This is many times caused due to leakages or complete disconnection of the anesthetic tubings. And also sometimes it is because the tidal volume setting is actually too low for the size of the patient. To solve this problem, it is good to just look carefully for all sources of leakages and disconnection and make sure that we restore them back to integrity. And on the tidal volume, increasing the tidal volume setting would be important until the sufficient pressure is generated. Now, when we have an alarm or a warning whereby we are having the bellows failing to fill completely, this is many times due to loss of drive gas pressure. And this can be solved by continued ventilation manually, just in order to make sure that we don't lose any life or cause any inconvenience. So we can just switch to ventilating manually until a further source of drive gas is available. And also, if there is failure of bellows to empty completely, this is mostly because there is an increased resistance to breathing due to obstruction that can happen on the anesthetic tubing. This can happen due to situation whereby there is kinking in the pipelines, and also maybe obstructions to the patient's airway through due to some secretions. To solve this problem, we can now also switch to manual ventilation and also make sure that we relieve any cause of obstruction on the pipelines, and also increase the patient pressure control to avoid any obstruction that is coming from the patient secretions. Moving forward, if there is sudden failure of bellows and there is no movement at all, many times it is a mechanical fault inside the ventilator, and we can also just turn to the manual ventilation via the self-inflating bag. And lastly, another alarm and warning that can occur is that the patient unexpectedly shows signs of light anesthesia. This can be identified when you see that the patient is showing signs that he or she is feeling some pain or something like that. So we should just make sure that the vaporizer is containing enough anesthetic agents and also at the required concentration to keep the patient in good condition. And also should just make sure that all connection to the patient are secure in the circuit to keep it intact to avoid any leakages. And moving to the next slide, I am going to explain to you the routine maintenance of anesthesia machine as it is also like any other machine that needs to be working perfectly in all conditions. So draining the halothane vaporizer every 3 months is important. This is so as it prevents the thermal buildup. Actually, this thermal many times leads to accumulation of bacterial membranes and associated events such as energy depletion. So when that happens, it happens that the gases that you're giving to the patient, they lose its energy. So it is good to actually drain the halothane. Another routine maintenance is to replace the oxygen sensor after 12 months, or when we feel that we see that the sensor has failed to pass the calibration. And to the oxygen concentrator, we can just go ahead and do routine and normal oxygen concentrator maintenance procedures, of which some of them are explained in some of our platforms. So, reaching this juncture, this is all we had for you on understanding the anesthesia machine, specifically the gastroventricular anesthesia. Thank you. Over to you, Sharon.
Thank you very much, Tim, for that well-detailed presentation. So, reaching this far, if we have any questions for us, please, you can paste in the chat or you can raise your hand. For those who are new members, please do share with us your email addresses in the chat so that we can add you to our emailing list, so that every time when we plan a call, we can send you a calendar invite so that you can get notifications. So looking at our time, we're past the time. So thank you all for joining us for this.
Thanks, everyone. Well done.
Thank you.
Please,
Bye.
we have a YouTube channel. Please visit, and you can see all the recorded oxygen talks from the past weeks. We also have maintenance videos, so you can check them out. You can also subscribe to our channel. We also have a Facebook page. Please do like. So to all our new members, don't forget to share with us your email addresses so that we can add you to our emailing list. And if you have any questions for us regarding today's presentation or any other presentation, please feel free to email to us through our email info@oxygenalliance.org. So until next time, it's bye from us.